What if I told you that the most violent and catastrophic events in a star's life create the most serene and beautiful displays in all of the cosmos? Right now, somewhere in our galaxy, a star is swelling to hundreds of times its original size, transforming into a glowing ember that will shine for millions of years. Hmm. This is not destruction. This is metamorphosis. This is the twilight that every star like our sun will one day experience. Are you ready to witness one of nature's most graceful transformations? Come with me as we explore the quiet majesty of red giants and discover why the end of a star's life might be its most magnificent chapter. Before we can understand the twilight, we must first understand the day. Every star you see in the night sky is engaged in a delicate balancing act that has continued for billions of years. Deep within their cores, hydrogen atoms are squeezed together under unimaginable pressure and heat, fusing into helium and releasing the energy that makes stars shine. This is the main sequence, the longest and most stable phase of a star's existence. Our sun has been in this phase for about 4.5 billion years, and it will remain there for another 5 billion more. But this equilibrium cannot last forever. The secret to a star's longevity lies in this balance between two opposing forces. Gravity wants to crush the star inward, to collapse it into a single point. The outward pressure from fusion pushes back, creating a stable sphere of glowing plasma. For billions of years, these forces remain perfectly matched. The star shines steadily, converting hydrogen into helium in its core at a rate determined by its mass. But every moment of light a star produces comes at a cost. It is slowly but surely consuming the fuel that keeps it alive. Think about that for a moment. Every ray of sunlight that has ever warmed your face, every sunset you have watched, every shadow cast by starlight is the product of this ancient dance. The light from our sun left its core tens of thousands of years before it reached your eyes, having spent that time bouncing through the dense interior before finally escaping into space. And all of it, all of that energy, comes from the gradual transformation of hydrogen into helium. But what happens when the hydrogen runs out? What happens when the dance must change? The timeline of a star depends entirely on its mass. Massive stars burn through their hydrogen fuel in just millions of years, living fast and dying young in spectacular supernova explosions. But stars like our sun are more patient. They sip their fuel slowly, maintaining their steady glow for 10 billion years or more. Right now, our sun is middle-aged, about halfway through its main sequence lifetime. It has converted roughly half of the hydrogen in its core into helium. The clock is ticking, but there is still plenty of time. But let us travel forward in time. Let us skip ahead 5 billion years and watch what happens as our sun's core begins to run low on hydrogen. The change is gradual at first, almost imperceptible. The core has been accumulating helium ash for billions of years, the spent fuel of fusion reactions. This helium just sits there, inert and lifeless, unable to fuse at the core's current temperature and pressure. As more and more hydrogen is converted, the helium ash pile grows larger. This simple fact will trigger one of the most dramatic transformations in the entire universe. You might wonder how such a slow change could lead to such a dramatic result. The answer lies in the delicate balance that has kept the star stable for so long. As the core fills with helium ash, it begins to contract under its own gravity. Remember, helium cannot fuse at these temperatures, so it generates no outward pressure to resist the inward pull. The core grows smaller and denser. And here is where something remarkable happens. As the core contracts, it heats up. Whoa! This sets the stage for the transformation we are about to witness. This is the moment of transition. The star is leaving the main sequence, departing from the stable existence it has known for billions of years. But this is not a sudden event. There is no explosion, no dramatic flash. Instead, the star begins a slow and graceful evolution that will last for millions of years. The hydrogen fusion that once occurred only in the core now migrates outward, forming a thin shell around the inert helium center. And in this shell, something extraordinary happens. The fusion rate increases. The star begins to produce more energy than it ever did during its main sequence lifetime. Take a moment to consider the poetry of this. The star, faced with the depletion of its core fuel, does not simply dim and fade away. Instead, it responds by burning even brighter. The shell of hydrogen fusion surrounding the helium core is thinner than the original core, but it is hotter and more energetic. It pours energy outward into the star's outer layers at an ever-increasing rate, and those outer layers, bombarded by this surge of energy, begin to respond in the only way they can. They begin to expand. The transformation into a red giant has begun. Imagine standing on a world orbiting this star and watching the changes unfold over millions of years. At first, you would notice the star growing slightly brighter in your sky. Then, almost imperceptibly, it would begin to grow larger. The expansion of a red giant is not like inflating a balloon. It is more like watching a slow-motion bloom, a cosmic flower opening its petals across a canvas of space and time. The outer layers of the star rise up and outward, pushed by the relentless energy flowing from the fusion shell below. And as they expand, they begin to cool. This cooling is the key to understanding why these stars are called red giants. You see, a star's color is determined by its surface temperature. Hot stars appear blue or white. Cooler stars appear orange or red. As the outer layers of our transforming star expand outward, they move farther from the heat source at the center. The surface temperature drops from thousands of degrees to just a few thousand. The star's light shifts from the yellow glow we know so well to a deep, ruddy crimson. The star becomes a red giant, glowing with the color of autumn leaves and distant embers. But do not let the cooler surface fool you. This star is more luminous than ever before. But how can this be? The answer lies in size. Yes, the surface is cooler, but the surface area has grown enormously. Imagine comparing a candle flame to a vast bonfire. The candle flame is hotter at its core, but the bonfire, spread across a much larger area, puts out far more total light and heat. A red giant can be hundreds or even thousands of times more luminous than it was on the main sequence, despite its cooler surface. It is a giant in every sense of the word. Let us talk about scale for a moment, because the numbers here are almost beyond comprehension. When our sun becomes a red giant in about 5 billion years, it will expand to roughly 100 to 200 times its current radius. Its surface will extend past the orbit of Mercury. Venus will likely be engulfed. Even Earth, depending on the exact details of the expansion and mass loss, might find itself inside the outer atmosphere of our dying star. Imagine that. The planet we call home, swallowed by the star that gave it life. But we should not think of this as pure destruction. Remember, the star is not exploding. It is transforming. The outer layers expand gently, majestically, like a cosmic exhalation. If you could somehow survive in the outer atmosphere of a red giant, you would find yourself in a place unlike anything in our current solar system. The density would be incredibly low, far thinner than the best vacuum we can create on Earth. You would be floating in a vast, glowing fog of hydrogen and helium, with the brilliant fusion shell burning somewhere far below, hidden in the depths. The expansion happens over millions of years, but it is not always smooth. As the star grows larger, its outer layers become less tightly bound by gravity. The balance between gravity and pressure becomes more tenuous. The star begins to pulsate, swelling and contracting in great rhythmic cycles. These pulsations can be regular, like a cosmic heartbeat, or irregular and chaotic. Some red giants vary in brightness by factors of hundreds or thousands over periods of months or years. They are breathing stars, alive with motion and change. And here is something beautiful to consider. As the star expands and cools, its atmosphere becomes a more hospitable place for molecules to form. In the hot photosphere of a main sequence star, molecules are torn apart almost as soon as they form. But in the cooler outer layers of a red giant, simple molecules can survive. Water vapor, carbon monoxide, titanium oxide, and many others appear in the star's spectrum. The star is no longer just a ball of plasma. It is becoming something more complex, something richer. It is evolving. This transformation is happening all around us in our galaxy right now. Some of the brightest and most familiar stars in our night sky are red giants. Arcturus, the fourth brightest star, glowing orange in the constellation. Aldebaran, the red eye of Taurus the bull. Betelgeuse, the magnificent red supergiant that forms the shoulder of Orion. When you look at these stars, you are witnessing stellar old age in all its glory. You are seeing what our sun will one day become. And there is something profoundly moving about that connection across time. While the outer layers of the star expand to enormous sizes, something very different is happening deep in the interior. Remember that contracting helium core we discussed earlier? It has not stopped contracting. In fact, as the star expands on the outside, the core continues to collapse on the inside. It grows smaller, denser, and hotter. The pressure at the center becomes immense. The core is being crushed by the weight of all the material above it, squeezed into a smaller and smaller volume. And this compression has a purpose. It is preparing the core for the next stage of fusion. The core temperature rises steadily as the core contracts. Tens of millions of degrees become hundreds of millions. The helium nuclei are moving faster and faster, colliding with ever greater energy. But helium is stubborn. It requires much higher temperatures to fuse than hydrogen does. The core must reach about 100 million degrees Kelvin before helium fusion can ignite. For less massive stars, this can take tens or even hundreds of millions of years. The star remains in this phase, with shell hydrogen burning and an inert core for a significant fraction of its total lifetime. This is the beginning of the red giant branch. Think about the structure of the star at this point. It is like a cosmic onion with distinct layers serving different roles. At the very center is the hot, dense helium core, inactive for now, but building toward a critical threshold. Surrounding this is the thin but incredibly energetic shell where hydrogen is fusing into helium. This shell is the engine that powers the star's enormous luminosity. Above that is the vast, extended envelope of the star, mostly hydrogen and helium, expanded to giant proportions. Each layer has its own temperature, density, and role to play in the life of the star. The hydrogen fusion shell is a remarkable place. It is thin compared to the size of the star, perhaps only a few % of the total radius. But within this narrow zone, the conditions are extreme. The temperature exceeds tens of millions of degrees. The density is enormous. The fusion rate is higher than it ever was in the original core. And this shell is not static. It slowly moves outward through the star as it consumes the hydrogen above the helium core. Double WAND. As it moves, it leaves behind a trail of freshly created helium, adding to the inert core below. The star is literally building its own eventual transformation from the inside out. But this journey is not simple or straightforward. In the deep interior, energy travels primarily through radiation, with photons bouncing from atom to atom in a random walk toward the surface. But in the outer layers, where the temperature is lower and the gas is less ionized, convection takes over. Huge convective cells form, carrying hot plasma up to the surface where it cools and sinks back down. The surface of a red giant is not smooth. It is a roiling, churning cauldron of convective motion. These convective cells can be truly enormous, sometimes comparable in size to the orbit of Earth. Imagine that. A single convective cell, one bubble of rising hot gas, as large as the distance from the Earth to the Sun. The timescales involved are equally impressive. It can take years or decades for material to complete one convective cycle from the surface to the base of the convective zone and back again. The red giant's atmosphere is in constant slow-motion turmoil. It is simultaneously chaotic and beautiful, a testament to the power of fluid dynamics on cosmic scales. The consequences of this convection are profound. It dredges up material from deep in the star, bringing it to the surface where it can be observed. Elements that were created through fusion in the core or shell can appear in the star's atmosphere, changing its composition. Astronomers call this the first dredge-up, and it is one of the ways that red giants enrich the interstellar medium with heavier elements. The star is not just evolving internally, it is also sharing the products of its nuclear alchemy with the galaxy around it. Even now, in this middle phase, the red giant is contributing to the cosmic cycle of matter. But the most important event is still to come. Deep in the core, that helium is getting hotter and hotter, closer and closer to the magic temperature where it can begin to fuse. When that moment arrives, the star will enter a new phase of its life, one powered not just by hydrogen, but by the fusion of helium into even heavier elements. The red giant is not done evolving. In fact, the most dramatic changes are still ahead. The core is a ticking clock, counting down to the moment when the next act of stellar alchemy will begin. And that moment is approaching, inevitably, inexorably, like the dawn after a long night. For stars with masses similar to our Sun, the ignition of helium fusion is not a gentle process. It is one of the most dramatic and violent events in all of stellar evolution, and yet it happens hidden from view, deep in the heart of the star where no telescope can peer. This is called the Helium Flash, and it is a moment of transformation so sudden and so powerful that it defies easy comprehension. To understand why it happens, we need to understand a strange state of matter called electron degeneracy pressure. And this strange physics will determine the fate of the core. As the helium core contracts, the density becomes extreme. The helium nuclei are packed so closely together that the electrons orbiting them are squeezed into a smaller and smaller volume. And here, quantum mechanics intervenes with one of its strange rules. The Pauli exclusion principle states that no two electrons can occupy the same quantum state at the same time. As the electrons are compressed, they resist further compression, not because of temperature or normal pressure, but because of this fundamental quantum rule. The electrons become degenerate, supporting the core against gravity through quantum pressure alone. This is both a blessing and a curse. The blessing is that degeneracy pressure halts the core's contraction, preventing it from collapsing into a black hole. The curse is that degenerate matter behaves very strangely. In normal matter, if you add heat, the pressure increases and the material expands. This acts as a natural safety valve for fusion reactions. But in degenerate matter, the pressure does not depend on temperature. It depends only on density. This means that when helium fusion finally ignites in a degenerate core, there is no safety valve. The core does not expand to regulate the fusion rate. Instead, the fusion rate explodes when the core temperature finally reaches about 100 million degrees. Helium nuclei begin to fuse. 3 helium nuclei combine to form 1 carbon nucleus in a process called the triple alpha process. The name comes from the fact that helium nuclei are also called alpha particles. At first, only a few reactions occur, but each fusion releases energy, which heats the core further, which causes more fusions, which release more energy. This is a runaway thermonuclear reaction, a fusion bomb going off in the heart of the star. In a matter of seconds, the fusion rate increases by a factor of billions. The energy released during the helium flash is staggering. For a brief period, the core is producing energy at a rate comparable to the entire luminosity of all the stars in the Milky Way galaxy combined. Hundreds of billions of stars worth of energy, all coming from a region the size of Earth. If you could somehow be there to witness it, the light would be beyond anything you could imagine. But here is the remarkable thing about the helium flash. Despite its incredible power, despite the unimaginable energy release, the outer layers of the star notice almost nothing. The flash is contained deep within. Why does the outer star not respond to this incredible outburst of energy? The answer lies in where the energy goes. In normal stars, energy generated in the core must work its way to the surface before it can be radiated away. But the helium flash happens so quickly that there is no time for the energy to propagate outward. Instead, almost all of the energy goes into lifting the degeneracy. The core heats up so much that the electrons are no longer degenerate. They are freed from their quantum prison. And once the degeneracy is lifted, the core can expand. The expansion cools the core, which slows the fusion rate, which allows equilibrium to be restored. Within a few hours or days, the crisis is over. The core is now stably burning helium into carbon and oxygen. The star has entered a new phase of its life called the horizontal branch. The violence of the helium flash is completely hidden from external view. If you were watching the star from a distant planet, you would see its brightness decrease somewhat over the following centuries as it adjusts to its new internal structure, but there would be no sign of the incredible drama that occurred at its heart. It is one of the universe's best-kept secrets, a cataclysm that happens in silence and darkness, known to us only through theory and calculation. The helium flash is unique to stars in a certain mass range, roughly between about half and 2 solar masses. More massive stars have cores that are hot enough to ignite helium before degeneracy sets in, so they transition smoothly to helium burning without a flash. Less massive stars will never get hot enough to fuse helium at all. But for stars like our Sun, the helium flash is an unavoidable rite of passage, a violent rebirth that happens in the hidden depths, invisible to the outside universe but fundamental to the star's continued evolution. It is a reminder that even in the serenity of cosmic processes, moments of intense drama are woven into the fabric of stellar life. To the helium flash, the star settles into a new equilibrium. It is now burning helium in its core and hydrogen in a shell surrounding that core. 2 fusion reactions, 2 sources of energy, operating simultaneously at different levels within the star. This phase is called the horizontal branch, named for where these stars appear on a graph that astronomers use to classify stellar evolution. The star is still large compared to its main sequence size, but it has shrunk somewhat from its peak red giant dimensions. Its surface temperature has increased slightly. It is still a giant, but a slightly smaller, slightly hotter giant. The helium fusion process is elegant in its complexity. It takes 3 helium nuclei, each with 2 protons and 2 neutrons, and combines them to form a single carbon nucleus with 6 protons and 6 neutrons. This is the triple alpha process we mentioned before. But it does not stop there. Once carbon is present, it can capture additional helium nuclei to form oxygen. And some of that oxygen can capture even more helium to form neon. The core of the star is becoming a cosmic forge, building elements heavier than helium for the first time. Carbon and oxygen, the foundations of organic chemistry, are being synthesized deep within the star. Think about the significance of this for a moment. Every carbon atom in your body, every oxygen atom you breathe, every calcium atom in your bones was created inside a star through processes like this. Not in our sun specifically, but in earlier generations of stars that lived and died billions of years ago. Those stars fused helium into carbon and oxygen, then later expelled those elements into space where they became part of the molecular cloud that gave birth to our solar system. You are made of stardust. This is not poetry. This is literal fact. You are the product of stellar nucleosynthesis, connected to the cosmos through the atoms that compose you. The horizontal branch phase lasts for a much shorter time than the main sequence, but it is still a significant period. For a star like the Sun, this phase might last 100 million years or so. That is a long time by human standards, but it is just a brief chapter in the star's multi-billion-year story. During this time, the star is relatively stable. It is not undergoing the rapid changes of the red giant branch. The dual fusion sources provide a steady energy output. The star shines peacefully, content in its new configuration, synthesizing carbon and oxygen in its core while continuing to convert hydrogen into helium in the surrounding shell. But as always, this stability cannot last forever. The core is consuming its helium fuel. Carbon and oxygen are accumulating in the center, building up into a growing inert core, just as helium did before. The helium fusion is slowly but surely burning outward, moving through the helium-rich layers and leaving carbon and oxygen ash behind. And as this happens, the carbon-oxygen core begins to contract under its own weight. Do you see the pattern? The same cycle that led to the helium flash is beginning again, but this time with carbon and oxygen instead of helium. The star is preparing for its next transformation. For some stars, this is as far as the fusion process can go. Stars with masses below, about 8 times the mass of the Sun, will never be able to fuse carbon in their cores. They simply cannot generate the temperatures and pressures needed, which are in the billions of degrees. The carbon-oxygen core will contract and heat up, but it will become degenerate before it can ignite carbon fusion. The core will cool into a dense, inert sphere called a white dwarf, supported entirely by electron degeneracy pressure. For these stars, including our Sun, the story of fusion is coming to an end. But that ending is still beautiful and full of wonder. As the carbon-oxygen core contracts, the helium fusion shell around it continues to burn. And above that, the hydrogen fusion shell also continues, creating a double shell burning structure. The star now has 3 distinct regions producing energy: the inert, contracting core, the helium burning shell, and the hydrogen burning shell above that. This complex internal structure drives the star toward its final phases. The outer envelope responds to the increasing energy output from the shells by expanding again. The star is becoming a red giant for the second time, entering a phase called the asymptotic giant branch. And this final red giant phase will be the most magnificent of all. The star swells to even larger dimensions than before, sometimes reaching sizes hundreds of times larger than the Sun. If our Sun were replaced by one of these stars, its surface might extend past the orbit of Mars. The luminosity increases dramatically. The star can become thousands of times brighter than it was on the main sequence. But this time, the expansion is not stable. The dual shell burning creates instabilities. The star begins to pulsate wildly, varying in brightness by large factors. Mass loss increases dramatically as the loosely bound outer layers are blown away into space by radiation pressure and pulsations. The star is beginning to dismantle itself one layer at a time. Deep within the red giant, a remarkable process is taking place. The dual shell burning structure is not just producing energy, it is also creating new elements, elements that were never present when the star first formed. This is nucleosynthesis, the cosmic alchemy that transforms simple hydrogen into the diverse array of elements that make up planets, life, and everything we see around us. In the depths of the red giant, carbon and oxygen are being forged, and through more complex processes, even heavier elements are being synthesized. The star has become a factory, churning out the building blocks of worlds. We have already discussed how helium fuses into carbon and oxygen through the triple alpha process and subsequent captures. But there are other processes at work as well. In the hydrogen-burning shell, proton-proton chains and the CNO cycle are converting hydrogen into helium, but they are also building up isotopes of carbon, nitrogen, and oxygen as intermediate products. These elements can be mixed into different parts of the star through convection, altering the star's composition. The star is no longer just a ball of hydrogen and helium. It is becoming chemically enriched, its interior a complex mixture of different elements at different depths. Some of the most fascinating nucleosynthesis occurs through a process called the slow neutron capture process, or the S process for short. In the helium-burning shell, some of the reactions produce free neutrons. These neutrons can be captured by existing atomic nuclei, gradually building them up into heavier and heavier elements. This is slow because it happens one neutron at a time, with long intervals between captures. Through the S process, red giants can create elements like strontium, yttrium, zirconium, and even heavier elements up to lead and bismuth. These are some of the same elements we find in the Earth and throughout the solar system. The production of these elements is not uniform throughout the star. They are created in specific zones where the conditions are right, particularly in the helium-burning shell. And here is where something remarkable happens. The intense heat and convection in the red giant can carry these newly created elements upward through the star to the surface. This is called dredge up, and it fundamentally changes the composition of the star's atmosphere. Elements that were locked in the deep interior are brought to the surface where they can be seen in the star's spectrum. The star is revealing the secrets of its internal alchemy to observing astronomers. This process has profound implications for understanding the chemical evolution of the galaxy. When we look at the spectrum of a red giant and see enhanced levels of carbon or other heavy elements, we are directly observing nucleosynthesis in action. We are witnessing the creation of the elements in real time. And because red giants eventually eject much of their mass into space, as we will discuss shortly, these newly created elements become part of the interstellar medium. They enrich the galaxy, becoming available to form new stars, new planets, new possibilities. The red giant is not just dying. It is giving back to the cosmos, contributing to the ongoing cycle of stellar birth and death. Some red giants, particularly those with initial masses near the upper end of the range, can create even more exotic elements. There are hints in some stellar spectra of the presence of technetium, an element that has no stable isotopes. All technetium isotopes are radioactive and decay relatively quickly. The presence of technetium in a star's atmosphere is proof that nucleosynthesis is happening right now, that the star is actively creating new elements and bringing them to the surface before they can decay. It is like catching the star in the act of its cosmic creativity, a smoking gun that reveals the ongoing transformation happening within. The diversity of elements created in red giants is truly remarkable. From carbon, the basis of organic chemistry, to oxygen, which we breathe and which makes up much of the Earth's crust and oceans, to heavier elements like iron, calcium, and silicon that form the building blocks of rocky planets. All of these elements were created inside stars, many of them in red giants similar to what our sun will become. When you hold a diamond or breathe in oxygen or look at the silicon in a computer chip, you are touching material that was forged in the heart of a dying star billions of years ago. The connection is tangible and profound, but the red giant's contribution to the cosmic inventory of elements is not finished yet. The elements being created and brought to the surface are still locked within the star. For them to truly enrich the galaxy, they must be released. They must escape from the star's gravitational embrace and disperse into the interstellar medium. And that is exactly what is about to happen. As the red giant continues to evolve, as its outer layers become less and less tightly bound, the star will begin to shed its envelope into space. It will create one of the most beautiful structures in all of astronomy. It will create a planetary nebula. But before we get there, let us spend a little more time appreciating the grandeur of the red giant phase itself. Red giants are among the most luminous stars in the galaxy. Their enormous size and high energy output make them visible across vast distances. If you were to travel to a distant corner of the Milky Way, hundreds or thousands of light years from Earth, many of the stars visible to your eyes would be red giants, shining brightly despite their great distance. They are cosmic lighthouses, beacons that can be seen from across the galaxy. And this visibility makes them incredibly valuable to astronomers. By studying red giants in other galaxies, we can measure distances, understand stellar populations, and trace the history of star formation across cosmic time. The brightness of red giants also means that they have a significant effect on their local environment. Any planets orbiting a red giant would experience dramatic changes. As the star expands and brightens, the habitable zone moves outward. Worlds that were once frozen ice balls in the outer solar system might briefly become warm enough for liquid water. But this is a temporary reprieve. The increased radiation from the red giant, particularly in the ultraviolet, would strip away atmospheres. The intense stellar wind would bombard the planets with particles. And for inner planets, the expanding star might simply engulf them. It is a bittersweet transformation, bringing temporary warmth but ultimate destruction. Let us imagine what it would be like to observe a red giant from a safe distance, perhaps from a world orbiting far enough out to avoid being consumed. The star would dominate the sky, perhaps spanning tens of degrees across. Its light would be deep red or orange, casting everything in a ruddy glow. During the day, the landscape would be bathed in this crimson light, creating an alien and surreal environment. The star's pulsations would be visible as slow changes in brightness over weeks or months, the sky growing brighter and dimmer in a cosmic rhythm. At night, if the planet had a night, the stars beyond would shine coldly against the darkness, a reminder of the wider universe. The wind from a red giant is not like the gentle solar wind we experience from our current sun. It is much more intense, carrying away mass at rates up to 1,000,000 times higher. This stellar wind is driven by radiation pressure and pulsations in the star's atmosphere. Dust grains form in the cool outer layers and are pushed outward by the star's light. The gas follows the dust, streaming away into space. Over time, the star can lose a significant fraction of its total mass through this wind. Some red giants lose as much as half their mass this way, shedding their outer layers in a slow but relentless exodus that prepares them for their final transformation. This mass loss has important consequences. As the star loses mass, its gravitational hold on its outer layers weakens. The escape velocity decreases. More and more material can be expelled into space with less and less effort. The process becomes self-reinforcing. The more mass the star loses, the easier it becomes to lose even more mass. And the material that is expelled does not just vanish. It forms a slowly expanding shell around the star, a circumstellar envelope that can be detected through its infrared emission as dust within it radiates the heat it absorbs from the star. The red giant is surrounding itself with a cocoon of its own shed material. Some of the most visually striking red giants are surrounded by complex structures created by their mass loss. Bipolar outflows, jets, and asymmetric shells have been observed around many evolved red giants. These structures suggest that the mass loss is not always smooth and spherical. Magnetic fields, rotation, or the presence of a companion star can shape the outflow, creating intricate patterns. When we look at these structures with modern telescopes, we see a level of complexity and beauty that was unimaginable just a few decades ago. Each red giant is unique, its mass loss sculpted by its individual history and circumstances into a work of cosmic art. The variability of red giants adds another dimension to their character. Many red giants are mirror variables or semi-regular variables, stars whose brightness changes dramatically and often unpredictably over time. Mira itself, the prototype of this class, varies by a factor of over 100 in brightness over a period of about 11 months. Imagine a star that dims to near invisibility and then brightens to naked eye visibility in a regular cycle. This variability is driven by pulsations in the star's envelope, sound waves that cause the entire star to expand and contract like a cosmic heartbeat. These pulsations can be complex, with multiple periods overlapping, creating an ever-changing light curve that astronomers study to understand the star's internal structure. There is something deeply moving about watching a red giant in all its glory. These are stars at the end of their lives, but they are not fading quietly into the night. They are blazing with light, pulsating with energy, shedding their material into space in a final act of cosmic generosity. They are creating elements and enriching the galaxy. They are visible across vast distances, inspiring wonder in anyone who takes the time to look up and observe them. And they are a window into our own future. When we look at a red giant, we are looking at what our sun will become. We are seeing the twilight that awaits our home star billions of years from now. And somehow, that connection makes them even more beautiful. As the asymptotic giant branch star continues to evolve, its internal structure becomes increasingly unstable. The dual shell burning, with helium fusing in one shell and hydrogen fusing in another, creates a delicate balance that is easily disrupted. And disrupted it will be. In a phenomenon called thermal pulses, the helium-burning shell periodically ignites in brief but intense outbursts, each one temporarily disrupting the star's structure and driving dramatic changes in its luminosity and mass loss. These pulses are the final gasps of fusion in the star's life, short-lived flares of nuclear burning that hasten the star's journey toward its end. The mechanism behind thermal pulses is related to the helium flash we discussed earlier, but it is less extreme and repeats multiple times. As helium accumulates in the shell between the hydrogen-burning shell and the inert carbon-oxygen core, the conditions for helium fusion improve. Eventually, a critical threshold is reached and helium fusion ignites explosively in the shell. This is not as violent as the initial helium flash because the material is not degenerate, but it is still a dramatic event. The sudden energy release causes the overlying hydrogen shell to expand and cool, temporarily shutting off hydrogen fusion. The star's luminosity increases dramatically for a brief period. Each thermal pulse lasts only a few hundred years, a brief moment in the star's multi-billion-year lifetime. But during that time, the star's structure undergoes radical changes. The energy from the helium shell pulse drives convection that extends deeper into the star than usual. This enhanced convection can bring newly synthesized elements from the helium burning zone all the way to the surface in what is called the third dredge up. Carbon, produced by helium fusion, is brought to the surface in large quantities. The star's atmosphere becomes enriched in carbon, and the star may transform from an oxygen-rich star to a carbon-rich star, fundamentally changing its chemistry and appearance. The transformation from an oxygen-rich to a carbon-rich star has visible consequences. In the cool outer atmospheres of carbon-rich stars, carbon combines with available oxygen to form carbon monoxide, locking up all the oxygen. Any remaining carbon can then form other molecules like polyatomic carbon chains and carbon dust grains. These carbon stars, as they are called, have distinctly reddish colors and are often surrounded by sooty clouds of carbon dust. They are cosmic soot factories, producing the graphite and other carbon compounds that will eventually find their way into interstellar space and perhaps into future planetary systems. The carbon in your body may have come from a star like this. The thermal pulses also drive intense mass loss. Each pulse increases the star's luminosity and pulsations, making it easier for material to escape from the loosely bound outer envelope. The star can lose mass at rates up to 10 millionths of a solar mass per year during and after thermal pulses, which may not sound like much but adds up over time. A star might experience dozens of thermal pulses over a few 100,000 years, each one stripping away more of the envelope. The star is literally tearing itself apart from the inside out, one pulse at a time. And with each pulse, it comes closer to revealing the hot core that has been hidden beneath all those layers of hydrogen and helium. Between thermal pulses, the star returns to a more stable configuration. The helium shell, having exhausted its fuel in the pulse, becomes inactive again. The hydrogen shell reignites as it cools back down from the disturbance. The star's luminosity decreases. For thousands of years, the star burns steadily, accumulating more helium in the shell and preparing for the next pulse. This interpulse period is a time of relative calm, a pause between the dramatic outbursts. But each interpulse is shorter than the last. The pulses are coming more frequently as the star's structure becomes more unstable. The end is approaching. The end is approaching. Some of the most fascinating red giants are caught in the act of thermal pulsing. Stars like R Sculptoris show clear evidence of multiple shells of expelled material surrounding them, each shell corresponding to a past thermal pulse. When we look at these stars with radio telescopes that can map the distribution of molecules like carbon monoxide, we see a beautiful spiral pattern in the expelled material. This spiral is created by the star's orbital motion if it has a companion, or by its rotation, creating a cosmic spiral as it sheds material pulse by pulse. It is a record of the star's final gasps, written in the distribution of gas and dust around it. The thermal pulse phase cannot last indefinitely. Eventually, the envelope becomes so depleted and the mass loss so intense that there is simply not enough material left to sustain shell burning. The hydrogen and helium shells shut down for the final time. The envelope, what remains of it, is almost entirely detached from the core. The star has reached a critical transition point. The long red giant phase, which has lasted for perhaps 100 million years or more, is coming to an end. What happens next will transform the star completely, revealing the dense hot core that has been growing at its center all this time. The stage is set for the creation of one of the most beautiful sights in all of astronomy. As the last of the envelope drifts away into space, something remarkable is revealed. The core, which has been hidden beneath layers of hydrogen and helium for billions of years, is finally exposed to the universe. It is tiny compared to the red giant that surrounded it, perhaps only the size of Earth, but it is incredibly hot and dense. The surface temperature exceeds 50,000 degrees or more, making it one of the hottest stellar objects in the galaxy. And from this exposed core, a flood of ultraviolet radiation pours out into space, radiation that has been trapped inside the star until now. This ultraviolet light is about to illuminate the expelled material in spectacular fashion. The material that was expelled during the red giant phase, particularly during the thermal pulse phase, now forms a shell or complex structure around the star. This gas is still relatively close to the star, perhaps a few light years away at most. And when the ultraviolet radiation from the exposed core reaches this gas, it ionizes the atoms, stripping electrons from hydrogen, oxygen, nitrogen, and other elements. The ionized gas absorbs the ultraviolet photons and re-emits the energy as visible light at specific wavelengths. The shell begins to glow. The planetary nebula has been born, and it is one of the most beautiful objects in the entire cosmos. The term planetary nebula is a historical misnomer. When these objects were first discovered through early telescopes, they appeared as small, round disks similar to planets. But they have nothing to do with planets. They are the glowing shells of expelled gas surrounding dying stars. Each planetary nebula is unique, shaped by the mass loss history of the star, by rotation, by magnetic fields, and sometimes by the presence of a companion star. Some are nearly spherical. Others are bipolar, with two lobes extending from opposite sides of the central star. Still others are irregular or multipolar, with complex structures that hint at a violent and chaotic ejection process. The colors of a planetary nebula are determined by which elements are present and how they are ionized. Hydrogen emits red light when its electrons recombine. Oxygen emits blue-green light. Nitrogen emits red light at a different wavelength than hydrogen. Sulfur emits deep red light. When you look at a color image of a planetary nebula, you are directly seeing the chemical composition of the expelled material. The green glow is oxygen. The red is hydrogen and nitrogen. The blue is helium and oxygen. The planetary nebula is a cosmic art piece painted in the colors of the elements themselves, a visible testament to the nucleosynthesis that occurred in the star's interior. The planetary nebula phase is brief compared to the star's total lifetime. The nebula is illuminated only while the central star remains hot enough to ionize the gas. As the core cools and dims over tens of thousands of years, the ionization weakens and the nebula fades. Meanwhile, the expelled gas is expanding outward at speeds of tens of kilometers per second. Over time, the nebula grows larger and more diffuse. Eventually, perhaps 50,000 years after it formed, the nebula has expanded and faded so much that it can no longer be detected. The gas merges with the general interstellar medium, dispersing the nucleosynthesis products from the dead star throughout the galaxy. The cycle continues. Some of the most famous objects in amateur astronomy are planetary nebulae. The Ring Nebula in Lyra, visible through small telescopes as a ghostly smoke ring. The Dumbbell Nebula in Vulpecula, shaped like a cosmic hourglass. The Helix Nebula in Aquarius, sometimes called the Eye of God, staring back at us from 1,300 light-years away. Each of these objects was once a red giant star like the ones we have been discussing. Each one represents the final breath of a star, the last act of a cosmic drama that played out over billions of years. And each one is enriching the galaxy with the elements created during the star's lifetime, ensuring that future generations of stars and planets will have access to a richer chemical inventory. The central star of a planetary nebula, the exposed core, is on its way to becoming a white dwarf. It is no longer producing energy through fusion. The nuclear fires have gone out completely. All that remains is the intense heat left over from billions of years of fusion and gravitational contraction. This heat will gradually radiate away over billions of years, and the star will cool and dim. But for now, in the planetary nebula phase, the central star is still incredibly hot and bright. It is a tiny beacon at the center of a cosmic flower, the last gasp of light from a star that has reached the end of its fusion-powered life. There is a profound beauty in planetary nebulae that goes beyond their visual splendor. They represent transformation and renewal, death and rebirth. The star has died in the sense that fusion has ceased, but in dying, it has created something beautiful and given back to the universe. The elements it forged are now free, available to be incorporated into new stars and planets. Perhaps, billions of years in the future, some of those atoms will become part of living organisms on a distant world. The planetary nebula is not an end. It is a transition, a bridge between one generation of stars and the next. It is the universe's way of ensuring that nothing is ever truly lost. When the planetary nebula has faded and dispersed, what remains is the core, now called a white dwarf. This is the final state for stars like our Sun, the end point of billions of years of evolution. Dwarf is unlike any object we encounter in everyday life. It is roughly the size of Earth, but contains a substantial fraction of the original star's mass, typically around half a solar mass. This means the density is extraordinary. A teaspoon of white dwarf material would weigh several tons on Earth. The matter is so compressed that it has entered a quantum state where electron degeneracy pressure provides the support against gravity, the same pressure that briefly dominated during the Helium Flash. White dwarfs are incredibly hot when they first form, with surface temperatures exceeding 100,000 degrees. But they have no source of energy production. There is no fusion occurring in their interiors. They are simply cooling embers, radiating away the stored thermal energy accumulated over billions of years of fusion. The cooling process is extremely slow. A white dwarf takes billions of years to cool to the point where it is no longer visible, eventually becoming a theoretical object called a black dwarf. However, the universe is not old enough for any black dwarfs to exist yet. Every white dwarf that has ever formed is still glowing, still cooling, still making its presence known to the cosmos. The composition of a white dwarf depends on the mass of the progenitor star and how far fusion progressed. Most white dwarfs, those from stars similar to our Sun, are primarily made of carbon and oxygen. They are the ashes of helium fusion, the elements that accumulated in the core during the horizontal branch and asymptotic giant branch phases. More massive progenitors might create white dwarfs with cores of oxygen, neon, and magnesium. Less massive stars might create helium white dwarfs, but regardless of composition, the structure is the same. A degenerate core supported by quantum pressure, surrounded by a thin, non-degenerate atmosphere of lighter elements, all compressed into a sphere the size of a planet. White dwarfs have been found with all sorts of interesting properties. Some have strong magnetic fields, thousands or millions of times stronger than Earth's field. Some are pulsating, varying in brightness with periods of minutes or hours. Some are in binary systems with other white dwarfs or with main sequence stars, leading to complex interactions and mass transfer. And some white dwarfs have atmospheres contaminated with heavy elements like calcium, iron, and silicon. This contamination is thought to come from asteroids or small planets that wandered too close and were torn apart by the white dwarf's immense gravity, raining their material down onto the star's surface. These are the last meals of a dead star. In binary systems, white dwarfs can experience a sort of second life. If a white dwarf has a companion star that is evolving into a red giant, material from the giant's extended envelope can be captured by the white dwarf's gravity. This material spirals inward, forming an accretion disk around the white dwarf. As the material falls onto the white dwarf's surface, it heats up and can trigger nuclear fusion in the accreted layer. This can lead to nova explosions, where the surface of the white dwarf suddenly brightens by thousands or millions of times as the accreted hydrogen ignites. The nova blows away the accreted material, and the cycle can repeat, sometimes regularly, sometimes sporadically. In rare cases, if the white dwarf is in a binary system and accretes enough material, It can approach a critical mass limit called the Chandrasekhar limit, about 1.4 solar masses. At this mass, even electron degeneracy pressure cannot support the white dwarf against gravity. The core begins to collapse and the compression ignites carbon fusion throughout the star almost simultaneously. The entire white dwarf undergoes a runaway thermonuclear explosion, a Type Ia supernova, one of the brightest events in the universe. The white dwarf is completely destroyed, leaving no remnant behind, but creating an enormous amount of iron, nickel, and other elements that enrich the galaxy. It is the final, ultimate contribution of a low-mass star's lineage. But for most white dwarfs, including the one our Sun will become, the future is quieter. They will simply cool and fade over trillions of years, slowly transitioning from white to yellow to red to brown, becoming dimmer and dimmer until they radiate only in the infrared and finally become invisible. They will become black dwarfs, inert spheres of degenerate matter drifting through the galaxy like cosmic fossils. But even then, they are not truly gone. They still contain the matter of the original star, the atoms that were part of a vibrant, fusion-powered object for billions of years. They are monuments to stellar evolution, markers of stars that once shone brightly in the night sky. The existence of white dwarfs teaches us something profound about the nature of matter and energy. It shows us that quantum mechanics, the physics of the very small, plays a critical role in the structure of stellar remnants. It demonstrates that matter can exist in extreme states utterly foreign to our everyday experience. And it reminds us that even after a star's fires have gone out, even after fusion has ceased forever, the star's legacy persists. The white dwarf is a monument. The planetary nebula enriched the galaxy. The elements created during the star's life are now part of new worlds and perhaps new life. The star may be dead, but its influence continues to shape the cosmos. Everything we have discussed in this journey is not just abstract astronomy. It is the future of our own sun, and by extension the future of our solar system. In about 5 billion years, the sun will leave the main sequence and begin its transformation into a red giant. The process will be gradual, almost imperceptibly slow at first. The sun will brighten by about 10% over the next billion years as its core slowly contracts. But then the changes will accelerate. The hydrogen in the core will be exhausted. Shell burning will begin. And the sun will start to swell. Everything we know and love about our solar system will be transformed in ways both beautiful and terrifying. As the sun expands, the inner planets will experience dramatic climate changes. Earth, if it survives, will become uninhabitable long before the sun actually engulfs it. The increasing solar luminosity will heat the surface, causing the oceans to evaporate. Water vapor is a greenhouse gas, so this will further accelerate the warming in a runaway process. Within 1 billion years or so, Earth will become a scorched, lifeless rock with temperatures hot enough to melt lead. Any life that exists will have to migrate to the outer solar system or leave entirely. The Earth we know, the blue marble of water and life, will become a Venus-like inferno, baked under the increasingly fierce glare of our dying star. Mercury will almost certainly be consumed by the expanding sun. Its orbit is small enough that even a modest expansion will engulf it. Venus will likely meet the same fate. The question of whether Earth will be swallowed is more uncertain. It depends on the exact details of how much mass the sun loses during its red giant phase and how that mass loss affects the orbits of the planets. If Earth does survive being engulfed, it will be a charred cinder orbiting within or just beyond the outer atmosphere of the red giant sun, bathed in searing heat and intense stellar wind. The fate of our home world is uncertain, but its habitability is not. Earth as we know it will be long gone, but even as the inner solar system is destroyed, The outer solar system will be transformed in surprising ways. The moons of Jupiter and Saturn, currently frozen ice worlds, will receive much more heat from the red giant sun. Temperatures on these moons might rise enough for liquid water to exist on their surfaces. Europa, Enceladus, Titan, and other frozen worlds could briefly become habitable oases in the outer solar system, warm and potentially life-bearing for a few 100 million years before the sun fades again. It is a bittersweet twist. The death of the inner solar system could create the conditions for life in the outer reaches, a temporary reprieve, a second chance for habitability in an unexpected place. The sun will remain a red giant for about 1 billion years, passing through the phases we have discussed. It will experience the helium flash, though no one will be around to observe it directly. It will burn helium in its core, creating carbon and oxygen. It will ascend the asymptotic giant branch, experiencing thermal pulses that drive intense mass loss. Slowly, gradually, the sun will shed about half of its total mass into space, creating a glowing shell of expelled material. And then, after 1 billion years of red giant evolution, the sun will expose its hot core. The ultraviolet radiation from this core will illuminate the expelled gas, creating a planetary nebula centered on our former star. What will this planetary nebula look like? We can only speculate, but it will likely be similar to other planetary nebulae we observe. Perhaps it will be roughly spherical, shaped by the relatively gentle mass loss from a single star. Or perhaps the sun's rotation, or the influence of the planets, will create asymmetries in structure. Imagine looking back from a distant vantage point and seeing the sun's planetary nebula glowing in the colors of hydrogen and oxygen, a cosmic flower blooming in the darkness of space. This will be the sun's final visible act, a last burst of beauty before it fades into the long twilight of the white dwarf phase. It is both an ending and a transformation. The white dwarf that will be the sun's final form will be a small, dense object made primarily of carbon and oxygen. It will be hot at first, over 100,000 degrees, slowly cooling over billions of years. The outer planets, or what remains of them, will orbit this white dwarf in the darkness. The solar system will be a ghost of its former self, a collection of cold worlds orbiting a dying ember. But even in this final state, the sun will not be without interest. Distant astronomers in other star systems might study our white dwarf, observing its cooling curve and perhaps detecting the remnants of the planets in its spectrum. The solar system will be a relic, a fossil record of a star's entire life cycle. But we should not mourn the sun's eventual fate. 5 billion years is an almost incomprehensible length of time. Humanity, if it still exists in anything like its current form, will have evolved beyond recognition. We may have left Earth long before the sun becomes a threat, spreading throughout the galaxy or even beyond. The death of the sun and Earth is not a tragedy waiting to happen. It is the natural conclusion of a magnificent cosmic story that we are privileged to be a part of. And in its death, the sun will give back to the galaxy, enriching the interstellar medium with carbon, oxygen, and other elements. Perhaps those atoms will become part of new worlds, new stars, new life, continuing the eternal cycle that connects all of us to the cosmos. And so, our journey through the twilight of stellar life comes to an end. We have witnessed the transformation of ordinary main sequence stars into magnificent red giants, glowing with the soft light of ancient embers. We have seen them forge new elements in their cores, experience dramatic thermal pulses, and finally shed their outer layers to create planetary nebulae of breathtaking beauty. We have followed the story from the first signs of core exhaustion to the final fade into a white dwarf, and we have glimpsed the future that awaits our own sun billions of years from now. Red giants are not symbols of death. They are symbols of transformation, of giving back, of the eternal cycle that connects stars to planets, to life, to the universe itself. The next time you look up at a red giant like Betelgeuse or Arcturus, remember that you are witnessing one of the most beautiful phases in the life of a star. You are seeing stellar old age in all its glory. And you are connected to that star through the atoms in your body, atoms that were forged in stars just like it. What will you see differently now when you look up at the night sky?